26E number 1. In Tart's experiment, the null hypothesis says that blank, you fill in the blank using one of the options below. The data are like 7,500 draws from the box 0001. The data are like 7,500 draws from the box 001. The fraction of 1 in the box is 2006 to 7,500, or the fraction of 1s among the draws is 2006 out of 7,500, or ESP is real. So does number 1 fit? Yes. Does number 2 fit? No, the proportions are wrong. Does number 3 fit? No, we don't know what's in the box. Does number 4 fit? No, why not? Does only one of them work? No, because I would have said yes on number 4. We can shoot. Oh, closed my book. Is ESP real? No. Well, we don't think so. Sorry, I lost my page. So the fractions of 1s among the draws is 2006. Does it give an explanation? What does it say? For 4. No, so number 1. So it just says the answer is 2, and then it explains it. Or 1, yeah. Huh. But I wonder why 4 isn't correct. Because isn't the fraction of 1s oh, I see. I see. So the null hypothesis. So 4 is true, but it's not the null hypothesis. The null hypothesis says that, okay, that makes sense, that the data is going to be sum of the draws out of that box. Okay, number 6. Another ESP experiment used the 10-choice trainer. This is like Aquarius, but with 10 targets instead of 4. Suppose that in 1,000 trials, the subject scores 173 correct guesses. So my null hypothesis says that 100 is equal to 173. Why did I pick 100? It's 10% of 1,000. Right? So that's what we expect. If you play this game 1,000 times, you're expected to be right 100 times. Now, if you get 173, is that far enough away from 100 to explain that ESP works? Well, I don't know. We've got to figure it out. So we take, actually, let's just do 10%, right? We expect 10% plus or minus a certain percentage. So the SD is going to be the square root of 0.1 times 0.9. So the square root of 0.1 times 0.9 gives me an SD of 0.3. What should I do with that? So anyway, this is going to be 10% is equal to 17.3%. So I need to create an SE. What SE do I want? SEP. Now, I could have done SEN. If I stuck with this, I could have done SEN. But the SEP makes more sense. Now, if you did it in terms of the SEN, that's okay. It should still work. Okay, so I'm going to divide this by the square root of 1,000. Turn that, oh my goodness. Hey guys, the square root of 1,000 is 31.6. So 0.3 divided by the answer. And I get 0.01%, or wow. I am all over the place the last couple days. So 0.9%. 10% plus or minus 0.9%. Okay. So I draw my normal curve. I expect 10%. I actually got 17.3%. So I subtract those and I get 7.3, and I need to divide that by 0.9486. So 7.3 divided by the answer. Oh, dang it. Divided by 100. So I get 6.7 SEs. What is the area to the right of 7.7 SEs? 0. Our shade norm can't even give us a difference. If we shaded norm from -7 to negative infinity, we would get 0. Okay. So the SD of the box is the square root of 0.1 times 0.9. Make the z-test. We did. What do you conclude? So the difference between the expected value of 10% and the observed value of 17.3% cannot be explained by chance. So we reject the null hypothesis and we accept the alternative hypothesis, which means ESP is real. We just proved it. Yeah, great. Okay, number 7. A coin is tossed 1,000 times and it lands on heads 5,167 times. Is the chance of that head equal to 50%, or are there too many heads for that? Just looking at it, what would you say? Is being off by 167 a lot? Not really, but let's figure it out. So I'm going to do the SEP because that makes more sense. I expect 50%. I observed 67%. So do I use this to compute the SE, or do I use this to compute the SE? Well, so this is from the box. This is from the draws. We always use the box SD, except when we don't have it, right? If you don't have the box SD, then you use this to create the SD. Wait, did I say that wrong? No, I did it right. So, well, we think we have the box SD, right? And our point is to prove that this shows that the box is correct. That's what the null hypothesis says. So you always use the box SD except when you don't have it. When you don't have it, then you use this. So the square root of 0.5 times 0.5 is 0.5. And then I need to divide that by the square root of 10,000, which is 100. And I get 0.005, which turns into 0.5%. That is our SE. Our SE is 0.5%. So I draw my normal curve. So I use this to get the SD of the box, which is 0.5. I divide that by the square root of 10,000, which is like dividing by 100, and I get 0.005. But this is an SEP. And anytime you calculate the SEP, you need to turn it into a percentage. So my chance error is expected to be about 0.5%. Okay, so I expect 50%. My sample yielded 51.67%. How far is that in terms of SEs? So 1.67 divided by 0.5 is 3.3 SEs. Now, we understand what that means. Do we accept or reject the null hypothesis? We reject. Why? We're just too far to the right. If we have a significant result, we will reject after we get to 1.64. If we have a highly significant result, then we reject after 2.78. And we're even further away from that. So I do the shade norm, and when I shade norm from 3.3 to 5, how much area is there? And the answer is really close to 0%. So, is something wrong? Yes. We ended up with a highly significant difference. A difference that is so large, we do not believe that it can be explained by chance error. Now, is it possible that the chance error is that far? Yes, but it's highly improbable. Okay. Now, when I asked you originally, you told me that 5167 really wasn't that far off, right? 51% really isn't very far from 50%. So why did we reject? There's so many draws. If I only had 100 draws, would 51% be very far off? Well, let's see. 0.5 divided by the square root of 100 gives us 5%. Is 51.67 within 5%? Yeah. So if you do a lot of draws, then you can actually be quite accurate. But if you don't do very many draws, then you can't be very accurate at all. In fact, that's where we're going to head today after we finish this set. Okay, so Z was 3.3 and P was really close to 0. Number 8, repeat if the percentage is 50.67. So we're going to change this to 50.67, which means we get rid of the 1. So now I do 0.67 divided by 0.5, and I end up with a z-score of 1.34. I already know don't reject the null. We accept the null. How do I know I accept the null? Because 1.34 is less than 1.64, which is the breaking point for a 5% tail. Okay, but we need to compute the z-score, so I have to do a shade norm from 1.32, is that what it was? To 5. And when I do that, I get a right tail area of 9%. So P equals 9%. When P is 9%, what do we do? We accept the null hypothesis. And the null hypothesis says there is no significant difference between 50% and 50.67%. Okay? We cannot say that 50% is wrong. In fact, we kind of say 50% is totally plausible.